welcome to the first session of this morning's session. And so it's a pleasure to have with us here Shamit Kachru from Stanford, currently working in the mathematics of finance, but with great expertise in theoretical physics, especially string theory, cosmology, and condensed matter. And I think in the talk we will see a bridge between various topics, and so the title is A Tapestry of Mathematics, Theoretical Physics, and Quantitative Finance. So let's welcome our speaker.
Thank you. So first, can you hear me? Is it too loud? It's fine. Okay. I'm really happy to be here. It's remarkable to see what China is doing to support fundamental science and mathematics. It's a great thing to see. My talk is a bit of an outlier. This is a string theory session, so you should think of me as the light entertainment while you're still waking up. You can digest your coffee and listen to what I say, and then heavier matters will be discussed later in the morning. But to the extent that there's content, it will be about relationships between basic mathematics, theoretical physics, and finance. Because the talk's a bit of an outlier, let me start with an introduction. This conference is basically about computer science, math, and theoretical physics. My current research involves some intersections of math, physics, finance, and technology, but it is constrained by NDAs. And so I will not be telling you anything about my current research in this talk, which presented a challenge in designing the talk. But the organizers, when told this, instead of just letting me say no, approved instead that I should talk on broad connections between the disciplines I work in that are evident not in anything that we do now, but in work of the 20th century that involved these kinds of topics. And I'm optimistic after thinking about it long enough to write this talk, that there is enough there to show that maybe surprisingly for those of you who are more purely inclined, there are some pretty fruitful connections between physics and market dynamics. Some are precise, some are at the level of very vague analogies. If you know me, you know I'll prefer the vague analogies. And so I'll talk about that in this talk. Okay, so my burden first should be to tell you where we're going to go. And then if you get lost along the way, you'll have some kind of roadmap of where to expect to reconnect. Shortly, I'll dive into the basic hypothesis of the randomness of nature and of markets. This evolved in parallel, actually in finance before in physics, and work of Becquelier and Einstein. I'll jump forward a few decades to work of Black, Scholes, Merton, and Thorpe. Or another way to put this is connections between the work of Fourier on heat conduction and the way we think about pricing certain options in markets. And I'll describe what an option is if you don't know. It's mathematically pretty simple. It can be formalized. Most of this theory is free in the sense that it's Gaussian, and the world is non-Gaussian, right? In physics, we study CFTs that interact. And in this world, it was understood pretty early on, actually about the same time Wilson was studying the RG, that non-Gaussianity is going to be important. Fat tails exist in most interesting distributions, volatility of returns clusters. And one of the great discoverers of fractal geometry, Mandelbrot, played a really interesting role in uncovering this story. So we'll talk about that for a little while. And then finally, I'll close with something much closer to the way people think today. It will sort of lead to where people are today, though I won't be able to talk about that, which is work of Fama-French and factors, and some way to emerge a simple story from the rather complicated mess that we're going to see in the first 3 quarters of the talk. Yeah. Interrupt me at points where it's not clear. And I went backwards. Okay, before I dive into the first things with actual equation-full content, let me give you a brief prehistory. This is by way of justification of why applied things are interesting to pure theorists. Some of the seminal early history of probability theory actually came out of thinking about economics. There are books about an exchange of letters between 2 famous people, Pascal and Fermat. You've all heard of both of these people in the 1650s. And in these letters, they germinated many of the foundational concepts or questions of probability. Their exchange was inspired by the fact that a nobleman who enjoyed drink and gambling, right, dice games go back to almost human prehistory, had been in the sad situation of having a dice game interrupted some rounds into the game. He thought he was winning and he wanted more than the equal share of the pot. And he wrote to Pascal and said, how do we fairly divide up the spoils if our game was interrupted in a probabilistic dice game? So we don't really know who would have won in the end. And so this nobleman's inquiry to Pascal led to this very fruitful interchange between Pascal and Fermat. Maybe the first physicist to become a quant, somewhat surprisingly, was Sir Isaac Newton. There is a wonderful book by Thomas Levinson, a professor of the science of writing at MIT, about Newton's career after he turned 50. In his early 50s, Newton, fed up with various aspects of academia, left Cambridge to take up a position at the Royal Mint in London, where he eventually rose to the position of Warden of the Mint. One of the highlights of his national service was solving the problem of arbitrage. So at that time, kings had divine right, and they could decree what metals and currencies are worth. And royal decree in England undervalued silver relative to gold compared to what other parts of the world did. So the king is, of course, free to declare that God thinks that gold and silver are worth whatever they are, but humans will be humans. And so the result of this was sort of predictably a bustling trade, removing all the English silver currency so that English coins would disappear, going to the continent, exchanging them for gold, coming back, and making a perpetual silver machine. Okay, so this class of problems, relative value of currencies, which Newton identified and helped solve in England, actually continued into the 20th century. There was a famous Bretton Woods Accord after World War II that broke down in the 70s. And so, you know, this tradition of humans getting into trouble with financial exchange is old, and it goes back even to Newton. Newton did other less savory things when he was in this position. This book is really interesting, and I recommend that you read it if you like the history of science. Okay, let's start getting slowly into content. So one of the first three papers of Einstein's miracle year of 1905 explained the peculiar motion of pollen grains that had been observed by the Scottish botanist Robert Brown in 1827. So Brown was studying grains suspended in a fluid. He noticed that they move around. He realized rather quickly that that did not mean that they were alive and moving under their own volition, but he didn't know exactly what it did mean. Okay. And this picture sort of indicates the answer that Einstein came to. So Einstein observed that the pollen grain motion follows something like a diffusive process, that microscopic fluctuations of hypothetical particles, let's call them molecules in the fluid, if they were jostling around due to thermal excitation, could buffet the pollen grain and cause its motion. And this provided a measurable test of atomic theory with a few parameters and a model for randomness in nature. Okay, and the basic theory here, pretty simple. There's a random walk. So if you start at x equals 0 at time 0, the diffusion process will say the average value of x squared. You can't predict the position, stochastic, but will be 2 dt, where d is a diffusion constant. And it's determined by other things that are natural. It's determined by the strength of thermal fluctuations in the numerator and the viscosity drag in the denominator. So there's a fluid viscosity, a radius of the pollen particle, and so forth. So this is one of Einstein's miraculous papers. It's maybe the simplest. But in fact, a similar insight preceded his observation by 5 years. So Louis Becquelier, who was far less famous than Einstein throughout his life, was a mathematics PhD student at Paris in 1900. He was advised by Poincaré, so he had a certainly great advisor. And he was looking around for problems, and he happened to live across from the Paris Stock Exchange, or I think they call it a bourse for whatever reason in French. So, you know, befuddled by how to choose a good problem, he would wander over to the exchange to waste time and notice that the prices of certain exotic assets move around in some kind of peculiar and random way. Okay, and so what he proposed is that asset prices, what we'd call stock prices today, here's a chart of many of them fluctuating over time, so time is here, some kind of value is here. He proposed that they move quickly following new information, that in some approximation, notably the approximation where you can quickly write a paper, the information is random and sometimes good and sometimes bad. Okay. And so if it's random and perturbs the price up or down randomly, and if the informational events are uncorrelated with each other, there's new information uncorrelated with previous information, then you get a very nice probabilistic question with repeated events that are IID adding up to some dynamical system, right? So post-1905, we could make an analogy. Einstein has a pollen grain, the market has assets. Einstein has a position of the grain, the market has a price. There's a diffusion constant in Brown's experiment. There's a measurable quantity, not quite as microscopic, the volatility of motion in the case of asset returns. And the underlying dynamics is governed by molecular collisions in Brownian motion, and by something a little more esoteric, but that took on a more and more important role as the century proceeded, by information in the market case. Okay, so this analogy is reasonably obvious, and is at the foundation of much thinking until at least the 1970s in this kind of subject. So as a result of this kind of picture and the central limit theorem, basic classes and websites that are relevant to finance, okay, you can go to Google, or if you're too modern for that, you can go to OpenAI and ask about how do asset prices move. And one of the references it will give you is something called Investopedia. And there are these nice pictures of these sort of 1, 2, and 3 sigma motion, regions for an asset price. If you're awake, I suspect most of you aren't quite awake yet, you'll notice there has to be a conceptual refinement. What Bekele said can't really be right, because for most assets, not all, but for most assets, prices can't go negative. And so you don't want the price to do a random walk, but you could have the return percentage do a random walk. And this refinement was made by Osborne. Osborne himself had a really interesting career and deserves a talk. He did a lot of classified work for the US government, but that would be a separate talk. In any case, Osborne's hypothesis was that it's percent price changes, not price moves, that follow a random walk. And this means the distribution of asset prices is log normal, not normal. So this governs much basic financial theory. And the analogy I'd make for you is that this is the free field theory of markets. Okay. Okay, that's great. But let's go back to our hapless graduate student, Bekele. What was the question he was actually pursuing? You might guess that if you're a student of somebody like Poincaré, you will have high ambitions. And so he was after a more involved and sophisticated question than trying to make a fit of how random asset prices move. And he made his bold conjecture en route, and the bigger problem he was after was not solved for another 60 years. So I'm going to have to define a financial term. I apologize, but it's mathematically clean and it will lead to a beautiful equation. So there are these things called put or call options. You should think of them as follows. They give you the right, but not the obligation, to sell in the case of put or buy in the case of call, a security, meaning a stock, at a given price called the strike price on a given date, July 28th, okay? European options are exactly what I said. You have to exercise them on the date that you pick the expiry date, and you pay the strike price if you want to exercise them. American options are more complicated, and we're in China, so we will not talk about the American options. Now, because they're going to play an important role in the following bit of the discussion, I want to make sure the payoff structure is somewhat clear. Okay, we'll get to a clean math problem in a second. It's not that essential, but it's good to be clear about your definitions. We'll always focus on call options. That gives you the right to buy something at a given price at a given date. Okay, you say, in the future, I think this will be worth more than X, so I will pay you X at that date and get the thing. So here's the payoff structure if you've bought a call option. It's that if the price goes up a little bit, you'll break even. It has to go up a little bit because you paid something for the option. Okay. And if it goes up more and more, then on the date you exercise the option, you make more and more. You sell the asset, you bought it for the strike price, you make some money. If you can understand that structure, that's all you need to know to follow the rest of this section of the talk. Okay? So it's a basic bet. It's a bet that the price is going to go up. Now, parenthetically, like lots of things in economics, these were introduced for a good reason and then took on their own life. So they were introduced to serve an economic function that they and other smaller objects. For instance, I flew here on United Airlines. I was on a 787, United Flight 888. It had 400 people on it. United is in the customer service business, or maybe the business of transporting people, or maybe the business of maintaining planes. United does not, by and large, think of itself as being in the fuel speculation business. But to transport 400 Americans as we grow heavier and heavier is an expensive business in terms of fuel. And so if United wants to make sure that the things it controls aren't overwhelmed by the noise of whether there's a war in Iran, they need to hedge out the price of fuel. And so what they will do is use things like options and related assets to make a bet that if the price moves up too much, they'll have the option that guarantees that they don't have to pay too much. Okay. Now that was the original function of such economic beasts. I think it's fair to say, especially if you follow news in India, these are now often used by speculators for other reasons. And like I said, it's like financial markets in general. Humans will do what they do. Okay. So Becquelier saw early analogs of these options on various assets, selling them for different prices at the bourse. And he wondered at the slightly deeper question, not how do I price the stock or guess the stock price, but how do I price the option on the stock? So the estimate of how the asset price itself moves is clearly a step towards figuring that out. It's a simpler necessary step, but it's not the full answer. Okay, and in fact, this problem admits a beautiful answer. Instead of trying to derive it for you in this talk, I'm going to tell you the answer and then sort of motivate it and discuss some consequences. There's a beautiful partial differential equation that governs this problem in an approximation we'll discuss, called the Black-Scholes equation. I should define terms here. V is the rational price that you should pay for the option. If you pay this price, you're not a sucker, but you're also not getting a good deal. It depends on S, the asset price at a given time that you're buying the option, and the time itself explicitly, maybe. Sigma is the volatility of the underlying asset. R is the risk-free rate, and what that means is if you put your money in a Bank of America account, they'll give you some interest. So that's the amount that you get for free money, right? So that has to enter somewhere because you price the option relative to how much you would get for doing nothing and not buying the option. So here's the differential equation. There's a dV/dt. There's a volatility term. It looks complicated. It's not, and we'll unpack it last. And then there are two terms that depend on this risk-free rate. One that just says somehow the option is appreciating with the risk-free rate, and a correction term that depends on how the option moves relative to the asset, called delta. This equation was derived formally around 1970. By formally, I mean in a paper by Black-Scholes and simultaneously Merton. Also by Thorpe, many decades after Becquelier's work. It resulted in a 1997 Nobel Prize to Merton and Scholes. Black had already died. The story with Thorpe is pretty interesting, and again, it shows that economics is always an interesting subject. Thorpe had basically derived the equation about a decade earlier than the others, but he did not publish. Instead, he decided the equation was true and used it to build one of the first successful quantitative hedge funds. And the successors of his fund still live on and are very successful and very under the radar in Southern California. Amusingly, there are connections to math and physics already here. Black had an undergraduate degree in physics and always thought as a physicist. He thought of himself as a physicist. And Thorpe was actually a professor of mathematics, first at MIT, then at Irvine, and then around 50 he retired to do other things, not unrelated to his work. Okay, anyway, let's get some intuition about this equation. So there's a bunch of terms here, and we're going to try and unpack what they mean. The intuition that Black and Scholes added comes from something called a no arbitrage condition. Think back to Newton and the possibility of arbitrage, right? To get a fair price, you always want to avoid possibility of arbitrage. We should think of delta, dV/ds, the amount the option price moves relative to a move in stock price, as a factor that indicates how sensitive the option is to asset value. Okay, and another way to say this that financial people would like is if you were trying to make a fake synthetic option yourself by buying the asset, you'd hold this much of the underlying asset instantaneously instead of holding the option. Okay, then in the limit where we neglect volatility, we will not neglect volatility, but for now we will. Okay, so we drop this term, we move the terms with R to the other hand side of the equation, and we get an equation that says dV/dt, the way the option price evolves with time, is R, the risk-free rate, times V minus S delta. So what does this equation mean? We should be able to understand it if it's rational. That is correct. Yeah. I mean, in fact, of course, V is also set by the market, and we'll come back to that. Right? You don't solve nature does not solve the equation to set V as it would in physics. But okay, so the interpretation here of the simplified equation with no volatility is that the capital freed up by expending S delta to make a synthetic option, and if you invest the rest at the risk-free rate, is given by this quantity in parentheses, and by no arbitrage, the option has to accrue value at the same rate, or you just switch to the synthetic option. Okay, so this kind of logic is what allowed Black and Scholes to derive the equation. Thorpe was a mathematician and did it other ways. Good. So I'm going to assume, at least at a hand-wavy level, that explains these two terms. Now let's focus on this term, which is probably the interesting one. So this final sigma squared term incorporates random walk volatility, and it shows how the options value can gain from potential large swings in the underlying asset price, giving an advantage or disadvantage in volatile markets. This may not seem intuitive, like I said these words, and then there's that term, and you're like, what are you talking about? I promise it will be crystal clear in about 2 slides. Okay. Before I do that, I want to deal with boundary conditions. Unfortunately, there is at least one mathematician in the room, so I have to be slightly honest and put in the boundary conditions, or the equation is ill-posed. But they're pretty intuitive. For instance, suppose that we have this call option, the thing that says if the price goes above a certain number, you could sell, and buy it for only that number. So let's call the call option price C. The boundary conditions for this equation would take the following form. They're physically motivated. If the asset price goes to 0, the call is worthless because the company is bankrupt. So it's not going to move after that. It's like being dead. If the asset price has gone to infinity, just meaning a really large number compared to your strike price, you're definitely going to be in the money when you cross the date of expiry. Well, then the option is worth, well, you're going to sell the asset. What you'll do is you buy the asset for K and sell it for S at the time of expiry, big T. But the value is a little bit more because before the time, big T, you could actually have slightly less capital that you'd have to pay and invest it at the risk-free rate to compound. And so this is the appropriate boundary condition at finite times before big T. Okay, and then finally, at the PF time T, the date of expiry, where this discussion ends, either your price is bigger than K, the strike price, in which case you get S minus K, right? Or you haven't made it and you get 0. And I see that David managed to wake up. Hey. Okay, so this was the logic. The stock price goes to 0, worthless. If you're definitely in the money, it's worth S minus K up to a small correction. And finally, at expiry, yeah, there we go. Okay, so now let's make that last term completely intuitive. In the limit that the risk-free rate is negligible, an example for those of you who are old enough is most of the 2010s, where after the financial crisis, banks charge 0 interest to loan money. The equation simplifies. We can just set R to 0. And in fact, up to changes of name, it's the same as a simple equation that I think you're all forced to take in undergraduate PDE classes. It's the heat or diffusion equation. So we could rewrite it where we think of the option price V as temperature, du dt is d del squared u, and the del here is with respect to spatial coordinate. So u is a function of the spatial coordinate. That spatial coordinate you should think of as the log of S, the log of the asset price. Okay, and if you rewrite this in terms of S, you get the more complicated structure I had shown before. The fact that log S and not S is the right coordinate is precisely related to the fact that asset motion is log normal, not normal. It's Osborne's observation, right, that price moves percentage-wise are normal, but not asset prices themselves. The diffusion constant then, very unsurprisingly, given what we talked about with Einstein and Michellier, is identified with the volatility. Okay, so the non-interest terms in the equation are precisely diffusion equations. And then if you think like me, where you like initial conditions, so of course mathematically you can think however you want, but I think in terms of the heat equation with initial temperatures, in that intuition time is reversed. right? So what's happening is the option price reaches a definite boundary condition at the expiry date. And the diffusion that's happening is the value is diffusing through asset price space as you go back in time. Okay? Good. Now here's a fact. I was asked before by Kristen, what's a variable and what's told to you by nature in this equation. This equation is about what humans do in markets, so everything is told to you by nature. You don't get to solve for anything. But in the Black-Scholes model, where you're solving for something, given the options prices, right, which are actually things that you see in nature, you can instead the implied volatility parameter. What you do is you run the differential equation with different volatilities until your options price and your asset price match up. Okay? And so instead of viewing the equation as something you solve for the fair option price, you view it as something you solve for what the market thinks the volatility is. Okay, this leads to a concept of implied volatility. The model, because it was made to be simple for theorists, builds in as an input, prediction is the wrong word, it's just an input, that the volatility is a constant, so it should be the same as inferred from each value of the strike price if there's a given date of expiry. It's just sigma. Markets are real things priced by real people. It's a fact that the implied volatility is not a constant. There's a volatility smile. For the calls that we've been talking about, as you have higher and higher strike price, in fact, the implied volatility is going up and up in the real world compared to the differential equation. Okay, so the strike price is such that you grow at large deviations from current price. Is that clear? Okey-dokey. Now, in fact, there's not just a volatility curve, there's a volatility surface. Because you can also move the date of expiry. You could buy an option for July 29 instead of 28. And so there's this curvy thing that's typically drawn this way with a value of volatility above each strike price and above each date of expiry. Okay, and it has this sort of Batman helmet shape. So here's a question. Humans are irrational to some extent, but they're also rational to some extent. And as we discussed, Einstein and Becquelier and Black and Scholes and Merton and Thorpe are the free field theory of markets. And we know free field theory is always wrong. So what explains the curvature? What is the market pricing in that Black and Scholes ignore? Okay, so now we're going to come to another hero in our story, Mandelbrot. For those of you my age and above, you remember him because there are these big glossy books with pictures of fractals when you were growing up. He's very famous for pushing fractal geometry and maybe being the first person to propose it as a notion. But in the early 1960s, quite by accident, he became interested in distributions of asset prices. This may sound like an odd subject for somebody who is a relatively famous, in some sense, mathematician, but he had a history of studying odd mathematical things. He was eclectic in his interests. His PhD thesis, this is overly strong as a way of putting it, but I'd say it was motivated by distributions of word frequencies in language. So there's a law called Zipf's law that says if the first most common word in an English book is, I don't know, whatever it is, the or something, and the second most common word is maybe and, I don't know, what is the relative frequency of ands to those? And this law continues down the chain of word frequencies. So he tried to give an information theoretic explanation of the emergence of such laws in language in his thesis. In any case, somebody with such bizarre interests later in life, not surprisingly, became interested in economic in income and wealth distributions of various countries. And pursuing that latter line of research, he showed up at Harvard to give a talk. Okay. And I think I accidentally repeat this on the next slide, so let me just move there. So he was invited to the Harvard economics department when they learned he was working on this. And when he was talking to somebody in the economics department on a blackboard there, he saw what turned out to be a graph of cotton prices. The scholar he was talking to had used Harvard's library to find a century of history of cotton prices and was making plots. This resulted in a famous paper, unfortunately not by that economist, but by Mandelbrot, called The Variation of Various Speculative Prices. So here's some plots. I'm not going to go into the details of the paper, but I'll give you the spirit. One, again, sort of odd for a mathematician working for IBM, is a plot of wool price differences over 5 and 10-month periods, binned into various bins of the price difference. And it's plotted against the normal distribution. And I think you can see even in this grainy font, the distribution is not normal. And then another is a graph of inferred volatilities of cotton prices just gotten from measuring how much the price is moving over various regions in time in this century of cotton data. And it doesn't look constant to me. It also looks kind of spiky. So far from seeing evidence of Gaussian distributions, which just at that time were actually coming into real vogue at MIT in Chicago in the slow development of efficient market theory. So Samuelson was a big promoter of this, and then later people at Chicago. Mandelbrot saw evidence that fat tails, and even maybe an ill-defined volatility, were governing at least the distributions and data that he could find. So his ideas were regarded as a bit fantastical by leading economists of the time, sort of leading off into sort of Alice in Wonderland world where anything goes. Here's a quote from an MIT economist in a book. This is a preface to one of Mandelbrot's papers that they happened to publish in the book. Mandelbrot, like Prime Minister Churchill before him, promises us not utopia, but blood, sweat, toil, and tears. If he is right, almost all of our statistical tools are obsolete. Surely, before consigning centuries of work to the ash pile, we should like to have some assurance that all our work is truly useless. So it's good to be dispassionate about evaluation of ideas. In any case, based on empirics, what he argued is that returns are governed by non-Gaussian distributions, and then he gets more specific. And that volatility is not only not constant, but it itself has interesting statistical properties as a time series. It clusters. Okay, and just to give you an idea of what that means in vivid pictures, we're in China. I took a picture from an article by Zhang and Fang in Entropy, 2021. This is a picture of normalized in a certain sense Chinese stock index CSI 300 returns over a period of a few years. You can kind of see spikes. You'd probably tell by your eye that the spikes tend to cluster with each other. There's a really deep spike. If you're old enough that you were alive during COVID, you can guess what the deep spike is. So he made detailed proposals for non-Gaussianity. His advisor was a probabilist named Paul Levy, who had approved his exotic thesis topic. And maybe coincidentally and maybe not, his proposal involves something called Levy stable distributions with various parameters. Let me quickly tell you what a Levy stable distribution is. One of the great things about a Gaussian is that if you add Gaussians together, or if you do convolution of Gaussians roughly, you add Gaussian distributed variables together, you'll get another one. Okay, so convolution closes in that subset of distributions. These Levy stable distributions under some natural assumptions are the widest class of distributions that have that property. If you're Levy stable with the same Levy parameters, and you convolve two such things, you'll get a third such thing. And what that means is you can use finite samples of data and estimate something and then add them together, and it'll work nicely. So the point about these distributions is that while the Gaussian is a special example, it's not special just because it's one, it's very special. Almost all the other distributions in this family have much more extreme behaviors. Okay, so here's a famous example you do all know, though probably not from probability. It was studied by Cauchy. So it's called the Cauchy distribution. And it can be described vividly as follows. Let us imagine that this wall was infinite, and that I was blind and had a very strong bow, and that David would come up here and spin me around, and then I would fire the bow, and the arrow would hit the wall somewhere along its infinite extent, and we'll call the horizontal place it hits X. Okay? Well, then half the time I would just miss the wall. The other half of the time, the angle would be such that I would hit the wall somewhere. And the probability distribution governing that is this one. Okay, so the f of x is governed by this. You can prove this using trigonometry. It's not hard. You can quickly convince yourself that the mean diverges, right? You multiply by x, you integrate, you're going to get a problem. The variance also diverges. So this would not be a great distribution if you wanted a Gaussian theory of markets. A representative family of these is controlled by one parameter. There's actually another parameter I'm just hiding. I don't want to make fancier plots. The parameter lives between 0 and 2. We'll call it alpha. For values between 0 and 2, they're more peaked and have fatter tails, that is, they go out further, than a Gaussian, which arises when alpha equals 2. And for the other values of alpha away from 2, their tails are captured by a power law that's 1 over x to the alpha plus 1. So instead of being exponential decay, it's power law. Okay, now here's a plot that tells you why this has been spiritually influential work, even if it's hard to put real flesh on it. It's a little bit ridiculous to use the language I'm going to use, but reputable economists like at the CFA Institute, I think it's Certified Financial Analysts or something, as well as most newspapers, will occasionally refer to n sigma fluctuations that embrace the stock market after things like COVID. They use some local in time based on their data sample definition of volatility. Then they declare there's been an n sigma fluctuation and have a bunch of quotes by people whose banks went bankrupt talking about how this should never happen. Okay, and so here one of our friends from the CFA Institute made a plot of daily returns over about 50 some years. He has 15,000 some days here. And you'll see that, for instance, he has a lot of events at the center. There are also some 10 sigma events. And a little back of the envelope calculation tells you that those happen, maybe once in every 10 to the minus 10 histories of the universe so far. So we haven't been trading that long. Anyway, you can take from this what you want. But what most people do take from this is that despite the lack of precision, the returns are both too clustered and far too often in the tails for a Gaussian or efficient market theory to be correct. And so for that reason, Mandelbrot's ideas have had spiritual influence, okay? Not because anyone actually believes there's an underlying process that is governed by one of his distributions. Because it ties into a subfield of physics, I'll talk a little bit more about his ideas before moving on to things that have been more influential. So he also had ideas about volatility, that not only is it not constant, but that it clusters in time. And these have found more practical purchase in things people do in banks. Okay, so one practical use case has been to predict volatility, and then people actually have assets that let you insure against volatility. Again, of interest for all kinds of big market players who don't want to be betting on volatility, so they hedge it. So for instance, there's a famous class of models that I put here in equations, except with a typo. I'll correct the typo in a second. Called Garch models, generalized autoregressive conditional heteroscedasticity. Autoregressive meaning later times depend on earlier times. Heteroscedasticity means that the volatility is not constant. Okay, and they work as follows. You have an asset, the return, the percentage change in its price at time t is some bit for some reason God told you, your best algorithms have told you. And then it has a fluctuation, which you could call idiosyncratic or residual. And the claim is, in that situation, okay, there's no volatility here because you already know this bit. It might be 0, but you know it. And then the condition is sigma t plus 1, and somehow I have dropped the t plus 1. Squared is given by a constant plus a multiple of the previous residual plus a multiple of the previous volatility. Okay, so these are very simple models. They can predict present day time scale volatilities with about 70% correlation in some cases. So they're actually used by people. They improve slightly if you coarse grain to longer than 1 day timescales. And they, of course, exhibit volatility clustering. And that's not a deep property. It's because you explicitly see an autoregressive condition. Okay. Yes? Yeah, sorry. I said this should be a t plus 1. Equivalently, this could be t and these could be t minus 1. You're absolutely right, and I'm sorry. That's an important typo. The solution's less interesting if there's not. Okay, so then Mandelbrot and others worked to develop slightly more microscopic models that could explain why you get a Lippi distribution with volatility clustering in these statistics. Okay, just like the Brownian motion explains a Gaussian walk, right? What kind of motion would explain this? And the crucial underlying structure he came up with is the Levy flight. So I guess he must have liked his thesis advisor. So we consider a random walk, but instead of saying it's a random walk with step size 1, we have a drunk who has highly variable step sizes. Maybe he likes to jump when he's drunk. And so instead, at a given step, he draws from a distribution whose probabilities come from a Levy draw. So the probability that the step is of length bigger than x goes like 1 over x to the alpha. Okay. To accommodate volatility clustering, so that will give you a Levy distribution because there's the Levy stability property. To accommodate volatility clustering, you have to be a step more clever, or really two. The simplest class of models that would do this, it would combine volatility clustering with Levy flights using Garch models, is the following. This is what would appear if somebody wanted to write a really bad paper on the archive and get an answer, but the answer is completely implausible. And the way you would do this is you would choose an underlying Levy flight with a given alpha. You would model the returns then via random walk whose step size is not given by that Levy draw, but by multiplying by a Garch volatility. So there's a separable formula like this, okay, with sigma generated by that autoregressive model. It's inelegant. It will make a model that has clustering. The clustering is extraordinarily boring. It dies exponentially quickly, so it's not very convincing clustering. And the parameter t that governs the fall-off rate of the volatility clustering, the 2-point function, can be solved for explicitly in terms of the parameters a and b here. Okay. So that's a bad idea. Here's a better idea. It's more elegant, at least. It arises by distinguishing volume time from clock time. So humans work in clock time to some extent. Markets don't. Sometimes things don't trade at all, like on weekends. Sometimes there's a lot of trading, like after Apple announces earnings and their AI model still doesn't work. Okay. So in considering dynamics of assets, instead of talking about time, it could be more natural to consider time rescaled by volume of transactions, okay, instead of the clock time. And if you do that, then indeed, you can get things where a Levy flight with each Levy step taking in a unit of volume time instead of real time will achieve the same results, but with satisfactory power law fall off in the 2-point. So this is somehow more physical. It's a little more convincing. It pushes question 1 step back, which is why it is that for humans volumes cluster. It's a fact about humans, and it's probably because information clusters. But in any case. Yes, so this reduces the question of volatility clusters, volume clusters. This just says they're related. And so you predict one of them. Yeah, so then you have to go and solve why volume clusters and what the power law is. Okay, why did I talk about this? It's not of particular interest to me, but a small subfield of theoretical physicists, some of whom are quite distinguished, like Mr. Stanley, built a field on explaining these statistics models and trying to make an analogy with statistical physics. It's called econophysics. There is a book. Okay, last bit of my talk. So what do I think I've shown you in the first bit? I think I've shown you what seems rather complicated and ad hoc to provide a reasonable model of daily returns of an asset, even at the level of broad generalities, like what are the statistics of Apple stock prices as a function of time. You can try to do it. They're ad hoc hypotheses. They're sort of pulled out of nowhere. Empirically, they don't do particularly well. Here's a question a physicist would ask. Can we coarse grain away details to find simple frameworks that shed light on at least big picture questions if we cannot answer the more basic question? Okay, and here's the standard cartoon about that. So unfortunately, it was not physicists that did this, it was economists. Fama-French, starting in 1992, found a very fruitful simplified framework. Fama won the Nobel Prize in 2013 based in part on this work. So here's their basic idea, and it's one that would occur to many people, but they managed to put some mathematical flesh on it. Pretty simple mathematics, but still. Their idea was a few economic factors will govern stock prices. Okay, so when a price moves, there's information, but we can classify the kinds of information that are going to be most relevant and just reduce our attention to those broad classes of information that will govern most of the price moves. So they said there are 3 such factors. One is sometimes people are excited or pessimistic. The overall market will do something. That means every stock will do something. There's an overall market factor. One is small and big companies might behave differently. Suppose the US president randomly imposes and then unimposes tariffs. Well, Joe's software hut that only sells in Michigan and only builds its software in Michigan may not be affected by tariffs. But, Coke might be because they bottle in one country and ship the bottles. They probably don't do that, but I was making up an example. Okay, so there could be a size factor. And then value could be something that people care about. Maybe if a company is cheap relative to how much it earns versus expensive relative to how much it earns, people will pay differently for its stock. So they brilliantly suggested, let's decompose returns as the risk-free rate. Okay, no arbitrage says you always have that. And then a factor associated with the company multiplying market, how sensitive this company is to the market. A factor telling you how sensitive it is to the size. And a factor telling you how sensitive it is to value. Okay? And importantly, these three things are measurable, not the betas, which you have to compute, but things they multiply, because this you see in the newspaper. This, Fama-French told you what small minus big, SMB, means. They defined a portfolio of small and big companies, told you that that defines SMB, and you can measure it every day. And HML, high minus low value, or cheap minus expensive, they similarly defined in terms of a concrete thing you can measure. Okay? So they said, think of returns this way. There's factors, and there's a residual. Say again? Well, that was their hypothesis. If that doesn't work, we'll do something fancier. I'll come back to your question less flippantly in a few slides, Gary. Only for a second, though. Okay, so the Fama-French betas, the loadings under these three factors, the betas in the equation, then suffice to determine asset returns up to this epsilon. Okay, big deal. You could write that with only one beta too, right? I mean, you can always say something is x plus y, and I don't know x, and I don't know y. Big deal. So for this to be useful, it of course matters what fraction of the variability of returns the model can explain. Okay, in fact, the basic tool being used here, to Gary's point, is linear regression, right? You have a time series and you're regressing it against other data that's time dependent. Linear regression actually goes back to Gauss. And just as an aside, at this conference, talking to Yuri Schinkel, the mathematician who's giving his own talk right now, I learned that actually in the 1840s, Gauss ran a hedge fund out of Göttingen, because Gauss invested the Göttingen Widow Pensioners Fund. So he may have been using regressions in a very similar way in the 1850s, I'm not sure. In any case, we're doing regression. And so the statistics question is, what is the R squared of the fit to asset returns? And their points, which was a very good point, is that for individual assets, this is still terrible and there's no simplicity. But if you take diversified portfolios, if you take, let's suppose David is bullish on AI and has 20 AI stocks, and we say, can we explain how this portfolio of 20 stocks moves? If it's diversified enough, so probably actually not all AI, you can actually get values of R squared up to about 90%. The point being that the idiosyncratic bits that you can't get actually do wash out. They're company-specific information. And these three major factors affect everybody. And so there's some validity to the idea. Okay? And in that sense, it's a coarse-grained description. Now, here's the first complaint I would make, or Gary's complaint might be the first, but I think this complaint works even at the linear level, so I'd put it prior. There's a standard technique in linear algebra or the all machine learning algorithms, principal component analysis. It's a linear dimensionality reduction technique that transforms possibly correlated variables into new sets of orthogonal variables called principal components, ordered by the amount of variance that they can explain in the data. So the first principal component is the vector that has most of the variance, the second has the second most variance, they're orthogonal to each other, and so forth. So if we say X is a T by N data matrix, each column is some asset whose price you care about, each row is a time observation, and we mean center the columns, then what PCA does is it finds orthogonal unit vectors, we should normalize, V1 through Vn, such that the projection XV1 has maximal variance in this setup. The projection onto V2, for some V2 orthogonal to V1, explains the subleading next largest amount of variance and so forth. This way, they sound non-concrete. How do you figure these things out? There is a very simple way. You take the asset return time series, you compute their covariances. That gives you a covariance matrix. It turns out V1 is the leading eigenvector of that covariance matrix. V2 is the subleading eigenvector, and so on. So a reasonable skeptic, before getting to Gary's question, would say, isn't this just principal component analysis? You found a few good directions and they account for a lot of the variance and you get a high R squared and big deal. That has nothing to do with markets. And I think I can defend them a little bit. Given this big return time series, these are our T by N vectors. Fama and French say we're going to predefine 3Vs. They're defined by economic quantities. And then we're going to do the linear analysis using these 3Vs. And that gives some natural regression of returns. Principal component analysis would say we will compute the covariance matrix of these used as data. We will find a few statistical factors. They're orthogonal, they have no a priori meaning, and we will do a natural linear regression of returns. Okay, so the fact that these have a predefined economic significance means that they are a priori different from statistical factors. They're not just PCA. Nevertheless, you could do phenomenology. Okay, this has been said a little misleadingly. Here's the right way to say it, I think. What you should do instead is take say the first 3 Fama-French factors, take a couple of leading PCA factors. I would probably take 2 instead of 3, or I would take 5 economic factors and take 3 or 4 PCA factors, and then ask, how do the PCA factors move around in the vector space defined by the economic factors? And I think that's a fruitful point of view. I think intuitively, you can view the factors defined by statisticians as living in this vector space spanned by a few economic factors, but they do rotate around in time. And the reason that the Fama-French view has been useful to economists is that they're fixed things defined by economics. Okay? I'm almost out of time, and that's good because I'm almost out of slides. So let me give you an upshot here and then quickly summarize. We have collective modes in physics that summarize the behavior of many microscopic constituents. For some reason, this is a picture I got of lattice distortion. I guess what happens here is the orange things are supposed to be where the atoms are, and the blue things are the displaced atoms, right? And so one way to describe this is you give the position of each atom in a lattice wave. A better way would be to define phonons as collective motions of the entire collection. Okay. So I think the emergent economic factors with weights along various assets summarize the collective behavior of large collections of assets in the stock market. Okay, this is a weak example of emergent dynamics in markets, but I think the analogy is not completely without intuitive merit. 2 natural follow-up questions. They had 3 factors, why not more? Academia has interesting incentives. Every new factor leads to a paper. Then you get a paper by an eminent economist talking about how there are too many factors now because everyone's writing a paper. The rate of factor production in academic research is out of control is the first sentence in the abstract. So the idea admits generalization, and sometimes it's fruitful, and sometimes it's just somebody writing a paper. Now finally to Gary's question. Why only linear models? Because they're easy. Going beyond linear regression does lead us to interesting directions where much research has been focused in recent and even not so recent years. I'm not going to say much about it. If you tell a young enough child, like a Stanford undergraduate, about linear regression, they look at you blankly, and then you write down some equations, and they say, oh, you're studying a neural network of depth 1, and it all is clear. Okay, so linear regression is a neural network of depth 1. You've all heard about higher depth because it's all the rage. So the obvious thing here to get nonlinear functions is to go to deeper neural networks. There has been intense interest in ideas of machine learning and deeper neural networks. It generalizes regression. It allows for correlations. I'm not going to talk about it. Inference from less structured data has been of no less interest to people like the people I talk to now. Given that atmosphere, it's actually not surprising if you watch AI that research initiated by actually a Chinese quantitative hedge fund led to one of the most impactful recent developments in the AI markets. I mean, DeepSeek, at least in the US, caused a huge stir. And so it doesn't shock me. And I think this example bodes well for the idea that going forward, there will be at least interplay between cutting edge math and science and technology and what goes on in financial firms that they are not publishing until they spin off an AI research firm. That's all I had to say. I didn't try to convince you that anyone is predicting anything very deep in these slides. If they are, they're not going to tell you in a talk. But all evidence is certainly that AI algorithms or other alternatives may compete well with discretionary predictions of anything about markets by humans. Every now and then, the Wall Street Journal or Bloomberg or the New York Times does this thing where they interview 10 experts about what the market's going to do in 6 months, and the experts say things, and then 6 months later, the New York Times reporters throw darts, at a board to determine price motions, and then they compare the performance, and you can guess what happens in these comparisons. So we're not going to do worse using all this fancy technology, and maybe we'll do better. And in any event, there's a lot of science to do here. So thanks for your attention.
Any questions or comments? There's a question there.
Yeah, thank you. That was awesome. I have a slightly technical question. So these Levy distributions, I think you can think of as like fixed points of self-convoluting renormalization group flow. Do you ever see like this sort of dynamics? Like you start out with a particular distribution, and it sort of like income or something like that, and it settles into this. And then the second thing is do you see any like actual conformal field theories, or this is maybe like in nature, like any models like this, or?
Okay, really sadly, your question is a great question. There's an analog of our G-flow in these distributions, right, from coarse graining. I think I'm going to just say I'm not the right person to ask, but there is a source. I put the source here for a reason. I would look at the source, and that will give you the leading insights at a certain time into your question. And I'm happy to talk about it afterwards if you're still interested.
Formula this beta and epsilon. Yeah, no, I think I remember there's also some kind for alpha return that people talk about.
Say again?
Alpha beta.
Yeah. So if you're somebody who's trying to do prediction and you work for a company that thinks it has good predictions, I mean, I can say a little bit, right? I mean, in fact, what people do now using fancier techniques is they try to nail this residual, right? Nobody is like, we're happy to predict broad collections of motion collectively. Everyone wants to nail this residual. If you've nailed a bit of this residual, you rename it, you call it alpha. Then the equation looks like this, but there's an alpha and there's an epsilon, which is now smaller. And the whole business is trying to move the epsilon into the alpha. The alpha usually has a small percentage correlation with actual returns, but the fact that it's even finite is remarkable because markets are incredibly high, incredibly low signal to noise. So in that formalism, yeah, you would add an alpha here and it would modify the risk-free rate, but it doesn't change the essential discussion. Yeah.
Thank you for the very interesting talk. I have a question. What is your opinion about maybe using LSTMs or RNNs to predict sequences like stock prices? Or
So you were asking about large language models?
like recurrent neural networks or LSTMs?
I'm not going to answer your question.
Huh?
I'm not going to answer your question. Thank you. It's a great question. It's a natural question. I'm just not going to say anything about it.
Oh, okay.
Any more unanswerable or answerable questions? If not, let's thank our speaker and let's have tea.